The number that matters most in hurricane forecasting right now isn't wind speed, it's alignment. Specifically, whether a storm's internal circulation, the actual spinning engine driving everything else about it, stands up straight from the ocean surface all the way through the upper atmosphere, or sits tilted and sloppy like a spinning top about to wobble off its axis. NOAA scientists just spent years combing through 27 years of Hurricane Hunter radar data specifically to understand this one detail, because it turns out to be one of the clearest advanced signals that a storm is about to explode in strength. Right now, off the coast of Hawaii, Tropical Storm Lala is doing exactly that, sitting 440 miles southeast of Honolulu with 65-mile-per-hour winds, forecast to become a hurricane by Saturday, with the Big Island already under a hurricane warning. Meanwhile, in the Gulf, the remnants of post-tropical Storm Arthur are dragging life, threatening flooding across eastern Louisiana right now, with a real chance the system could actually regenerate off the East Coast within days. Today, we're breaking down exactly where both of these systems stand. The genuinely new science behind why storms suddenly explode in strength and why forecasters are treating this specific mechanism as one of the most dangerous, least predictable parts of the entire hurricane season. No exaggeration, just what NOAA, the National Hurricane Center, and the researchers studying this phenomenon are confirming right now. If you want to keep following both of these systems as they develop, subscribe and turn on notifications, because conditions are genuinely changing by the hour. A thumbs up helps this critical information reach more people who need it right now. Let's get into it. Let's start with Lala, because it's the more immediate, more serious threat on the board right now. According to the National Hurricane Center's most recent update, as of 11 p.m., Eastern Time, Tropical Storm Lala was moving west-northwest at 14 miles per hour with maximum sustained winds of 65 miles per hour, positioned approximately 440 miles east-southeast of Honolulu. Hawaii County, the Big Island, remains under a hurricane warning. ABC News confirmed directly that Lala is forecast to strengthen into a hurricane as it approaches the Big Island on Saturday, meaning this storm needs to gain just 10 more miles per hour of sustained wind speed, crossing from 65 to 74 miles per hour, to officially cross the threshold from tropical storm to hurricane, a jump that, given everything we're about to walk through regarding how these storms actually intensify, could genuinely happen within a matter of hours rather than days. It's worth pausing on that specific 9-mile-per-hour gap for a moment, because it illustrates something genuinely important about how hurricane classification actually works. The Saffir-Simpson scale, the standard system used to categorize hurricane intensity, draws a hard line at 74 miles per hour separating a tropical storm from a Category 1 hurricane. That threshold isn't arbitrary. It reflects a genuine physical shift in the kind of damage a storm becomes capable of, producing structural damage to roofing and siding, down to trees and power lines on a much broader scale, and considerably more dangerous storm surge potential along any coastline the storm approaches. A storm sitting at 65 miles per hour, as Lala currently is, remains genuinely serious, but a storm crossing that 74-mile-per-hour line transforms into an entirely different category of hazard, both in terms of the physical damage it can inflict and in terms of the specific emergency protocols, evacuation orders, shelter openings, and infrastructure shutdowns that local officials typically activate once that threshold is crossed. Now let's get into the actual science behind why storms make that exact kind of jump, because NOAA just published research that gives forecasters a genuinely new tool for anticipating it. According to NOAA's Atlantic Oceanographic and Meteorological Laboratory, researchers leveraged 27 years of radar scans collected by Hurricane Hunter aircraft, the specialized planes that fly directly into tropical storms and hurricanes, to gather data no satellite can capture, to reveal new insights into one of the most elusive phases of a tropical cyclone's entire life cycle, something called vertical alignment of the vortex. This is described directly as a critical precursor to rapid intensification, and the study represents the first time researchers have used this scale of decades-spanning radar observation specifically to identify the storm structure, environmental conditions, and rainfall patterns associated with a storm actually achieving this alignment. It's worth understanding exactly what this means in practical terms, because it's genuinely the mechanical heart of how a storm transforms from a disorganized mess of thunderstorms into a genuinely dangerous, rapidly strengthening hurricane. The most powerful tropical cyclones are characterized by what researchers call an aligned vortex, a strong circulation center that extends vertically and symmetrically from the ocean surface all the way up through the atmosphere. But many developing storms don't start out that way. They begin with their circulation tilted or misaligned, essentially leaning at an angle rather than standing straight up, and predicting whether a specific storm will actually straighten out into that fully aligned, dangerous configuration has long been one of the genuine challenges facing hurricane forecasters. This new research, built on nearly 3 decades of direct radar observation, gives meteorologists new indicators for recognizing exactly when a developing storm is likely to organize and intensify, precisely the kind of advanced warning capability that could genuinely change how much notice coastal communities get before a storm suddenly transforms into something far more dangerous. It's genuinely worth digging a bit deeper into why a tilted misaligned vortex behaves so differently from an aligned one, because it comes down to some fairly intuitive physics once you understand the basic mechanism. A hurricane draws its energy upward from warm ocean water, funneling that energy through a column of intensifying thunderstorm activity surrounding the storm's central low-pressure core. When that central core sits tilted, wind shear at different altitudes is essentially pulling different layers of the storm in different directions, disrupting the clean, efficient transfer of heat and moisture from the ocean surface up through the atmosphere. Once that tilt resolves and the vortex straightens into full vertical alignment, that same energy transfer becomes dramatically more efficient, allowing the storm to intensify far more rapidly than it could while still tilted. That's genuinely the physical mechanism NOAA's radar research was specifically designed to capture and characterize in far greater detail than had previously been possible, using decades of direct in-storm observation rather than relying purely on satellite imagery or computer modeling alone. Let's connect that science directly to the actual formal definition of rapid intensification, because it's worth being precise about the specific numbers involved. According to Climate Central's updated tracking, rapid intensification is formally defined as an increase in a tropical cyclone's maximum sustained winds of at least 30 knots, roughly 35 miles per hour, within a 24-hour period. There's a more extreme version tracked separately, called extreme rapid intensification, defined as gaining at least 50 knots, roughly 58 miles per hour, within that same single day. From 1980 through 2025, 190 separate Atlantic tropical cyclones experienced rapid intensification, and nearly a quarter of those, 46 storms, or 24%, actually reached that more extreme threshold. In 2025 alone, 4 separate Atlantic hurricanes, Erin, Gabrielle, Humberto, and Melissa, all rapidly intensified. It's genuinely worth pulling out Hurricane Melissa specifically from that list because it stands as the most recent and one of the most extreme examples of exactly what this phenomenon can produce. According to detailed tracking of that storm's life cycle, between October 25th and October 27th of 2025, Melissa flew through multiple hurricane classifications in rapid succession, ultimately topping out as a major Category 5 hurricane before making landfall in Jamaica. That's a storm that went from a considerably weaker classification to the absolute maximum intensity the Saffir-Simpson scale even measures within roughly 48 hours. And Melissa wasn't some kind of statistical outlier for that specific year either. 3 other 2025 storms, Erin, Gabrielle, and Humberto, all underwent that same rapid intensification process. That means, across just a single hurricane season, 4 separate storms all demonstrated the exact phenomenon this entire story is centered on. A genuinely striking clustering that helps explain why meteorologists have been pushing so hard in the time since to develop better forecasting tools specifically targeting this mechanism. It's worth understanding the specific ingredients that actually drive this kind of explosive strengthening, because they explain both why some storms explode and others simply fizzle out. First and foremost, sea surface temperature has consistently been identified as the leading factor behind storms strengthening fast. On average, a storm needs ocean surface temperatures of at least 80 degrees Fahrenheit to even form and strengthen at all, since that warm water provides the actual fuel a developing system needs to organize and intensify. During 2025, the Atlantic Basin, the Gulf, and the Caribbean Sea all ran warmer than normal throughout hurricane season, with some specific locations reaching as high as 85 degrees, sitting 3.6 degrees Fahrenheit above their typical averages. Beyond raw ocean temperature, a highly moist atmosphere and low wind shear both contribute directly to how quickly a storm can grow. Wind shear, specifically, can rip apart a developing storm at the top, physically preventing it from building the kind of vertically aligned symmetrical structure that NOAA's new radar research specifically identified as the critical precursor to rapid intensification in the first place. It's also worth understanding that ocean heat content matters in a way that goes beyond just surface temperature alone, a detail that connects directly back to why deep, warm water specifically matters so much to storms capable of sustained rather than brief intensification. A storm passing over warm surface water but comparatively cool water just beneath that surface layer will often churn that cooler, deeper water upward as it moves, a natural process called upwelling that can actually cut off a storm's own fuel supply mid-intensification, causing it to weaken even while surface temperatures ahead of it remain warm. By contrast, When warm water extends to genuine depth, meaning the entire upper layer of ocean, not just the immediate surface, sits at a temperature capable of sustaining intensification, a storm can continue drawing on that deeper heat reservoir even as it churns the water beneath it, sustaining rapid intensification over a considerably longer stretch than a storm passing over only a thin, superficial layer of warm surface water would be capable of. That brings us directly to why this particular season's overall atmospheric setup matters so much for understanding where genuine risk is actually concentrated right now. By June of 2026, El Niño had already begun developing in the Pacific, a pattern that would normally translate into a below-normal Atlantic hurricane season overall, since El Niño tends to generate elevated wind shear across that specific basin, the same suppression mechanism we've discussed in earlier coverage this season. According to ABC 13, Houston's tropical weather coverage, NOAA's own August update to the 2026 hurricane outlook has since dropped both the total number of named storms and the number of major hurricanes expected for the remainder of the season by one storm each, with a rapidly strengthening El Niño specifically identified as the primary driver behind that downward revision. But here's precisely the tension at the center of this entire story, the one worth genuinely internalizing. A below-average season driven by elevated wind shear across the broad Atlantic basin doesn't mean every single storm that does manage to form will remain weak or slow to develop. It means fewer storms overall are likely to successfully organize against that shear. The ones that do manage to find a pocket of genuinely favorable conditions, low shear, warm water, moist air, and the right structural alignment, NOAA's new research specifically helps identify, can still explode in intensity just as fast, or faster, than storms in a considerably more active season. CNN's own tracking of the 2026 season captured this exact dynamic directly, confirming that 3 named storms have formed so far this year, actually slightly ahead of the historical average of about 2 storms by the same point in the season, even while many forecasters continue anticipating this season overall won't behave like the more frenetic recent years by the time it officially concludes in November. Now, let's turn to what's actually happening across the Atlantic and Gulf right now, because there's genuine immediate activity worth tracking even within this broader, quiet season framing. According to ABC 13's most recent tropical weather update, post-tropical, Storm Arthur has officially dissipated as an organized tropical system, but its remnant moisture is continuing to track across eastern Louisiana today, where forecasters are warning of significant, and even life-threatening, flooding in some areas. That remnant system is then expected to spread northeastward into portions of Georgia and the Carolinas. Here's the detail that genuinely matters for anyone along the eastern seaboard specifically. The National Hurricane Center says environmental conditions actually appear favorable for some subtropical or tropical redevelopment on Friday or Saturday, as this system continues moving northeastward at around 15 miles per hour and eventually emerges offshore the east coast of the United States, out into the western Atlantic Ocean. Formation odds for that specific redevelopment scenario currently sit at 10% over the coming 7 days, a genuinely low probability but not zero, and worth watching, given how directly it would affect the eastern seaboard if it did occur. It's worth understanding what redevelopment or regeneration of a dissipated system actually means, because it's a genuinely different process from a brand new storm simply forming from scratch. When a tropical system weakens and loses its organized tropical characteristics, as Arthur has now done, its remnant moisture and any lingering low-level circulation don't necessarily vanish entirely. If that remnant system moves into an environment that once again becomes favorable, warm enough water, low enough shear, sufficient atmospheric instability, it can, in some cases, reorganize and redevelop into a new tropical or subtropical system, sometimes even retaining its original name, if forecasters determine the circulation never fully broke down, or occasionally being assigned a new name if the reorganization is significant enough. That's exactly the scenario. The National Hurricane Center is currently assigning a 10% probability to, as Arthur's remnants track northeastward and eventually reach the Atlantic waters off the east coast. Beyond Arthur's remnants, the National Hurricane Center is also tracking 2 separate disturbances in the Pacific. One tropical wave in the eastern Pacific is currently producing only a few showers and thunderstorms, and it's moving into a considerably drier environment, keeping its tropical development odds relatively low, around 20%. A second disturbance in that same basin carries a 30% chance of organizing into a tropical depression as it continues tracking west at 10 to 15 miles per hour. Neither of those 2 Pacific systems currently carries anywhere near the level of confidence or urgency that Lala's own forecast does, but both remain genuinely worth monitoring, given how quickly a system's development odds can shift once it moves into more favorable conditions, exactly the kind of shift NOAA's new alignment research is specifically designed to help forecasters anticipate earlier. It's genuinely worth revisiting, in this context, why rapid intensification specifically terrifies emergency planners more than almost any other single hurricane phenomenon, because the historical examples are genuinely sobering. According to research from the National Center for Atmospheric Research, Hurricane Helene needed just 2 days to grow from a relatively weak tropical storm into a major Category 4 hurricane by the time it made landfall in Florida in 2024, a storm ultimately blamed for roughly 250 deaths across several southern states. Hurricane Harvey similarly rapidly intensified as it approached the Texas coastline in 2017, submerging parts of the Houston area under unprecedented rainfall totals and causing an astonishing $160 billion in total damage. And Hurricane Michael offers maybe the single starkest illustration of exactly why this phenomenon remains so genuinely difficult to forecast, even with decades of accumulated research now behind it. When Michael became a tropical storm in the Gulf back in 2018, forecasters at the time expected its winds would top out at no more than 70 miles per hour. Instead, Michael crashed ashore the Florida Panhandle carrying winds of 160 miles per hour, a Category 5 equivalent storm that forecasters, using the tools available to them at that specific moment, simply hadn't been able to anticipate. That specific gap between what forecasters expected and what actually happened is precisely the gap NOAA's new radar-based vortex alignment research is trying to close. According to the study's own framing, the method was specifically shown to be useful in identifying which of a hurricane's multiple forecasted potential tracks was most likely to actually result in rapid intensification, giving forecasters a genuinely new additional layer of insight beyond the track and intensity, models that already existed. Separately, and in a genuinely complementary line of research we've discussed in earlier coverage, scientists at the National Center for Atmospheric Research have also developed a method specifically for predicting which storms are likely to undergo rapid intensification as far as 5 days in advance, a considerable improvement over the historically shorter warning windows forecasters have had to work with for this exact phenomenon. Together, these two research efforts represent a genuinely meaningful, ongoing push within the hurricane science community to close the gap that left communities along the Florida Panhandle with far less warning than they needed when Michael exploded from a 70-mile-per-hour tropical storm into a 160-mile-per-hour catastrophe. It's worth understanding a bit more about why this research push has become such a genuine priority across the broader hurricane forecasting community in recent years, beyond simply the handful of individually devastating storms we've already discussed. Track forecasting, meaning predicting where a storm will actually go, has improved dramatically over the past several decades, to the point where modern 5-day track forecasts are now roughly as accurate as 3-day forecasts were a generation ago. Intensity forecasting, by contrast, meaning predicting exactly how strong a storm will actually be at any given point along that track, has historically lagged considerably behind those track forecasting improvements. Rapid intensification represents, in many respects, the single most consequential piece of that intensity forecasting gap, because it's precisely the scenario where a storm can shift from a manageable, well-understood threat into a genuinely catastrophic one within a window far shorter than the time communities typically need to complete a full evacuation. Closing that specific gap through tools like the vortex alignment research and the 5-day rapid intensification prediction model represents genuinely one of the highest priority areas of active hurricane science research happening right now. There's also a genuinely useful, complementary piece of research worth mentioning here, distinct from the Atlantic-focused work we've already covered, because it illustrates just how global this specific scientific challenge actually is. Rapid intensification isn't a phenomenon confined to the Atlantic basin. Tropical cyclone. Horatio, tracked earlier this year in the Indian Ocean, rapidly strengthened into the equivalent of a Category 5 hurricane. Satellite imagery capturing the storm's explosive development over just a matter of hours, that kind of cross-basin. Documentation, storms undergoing this same explosive intensification process in ocean basins as geographically distant as the Indian Ocean and the Atlantic, reinforces just how universal the underlying physical mechanism actually is: warm water, low shear, moist air, and vertical alignment, regardless of which specific stretch of ocean a storm happens to be developing over. So, pulling this entire picture together, what's the honest, complete summary of where things stand right now, both with the storms actually in play and with the broader science surrounding why storms explode the way they do? Tropical Storm Lala sits 440 miles southeast of Honolulu with 65-mile-per-hour winds, forecast to cross the hurricane threshold by Saturday as it approaches the Big Island, which remains under a full hurricane warning right now. The remnants of post-Tropical Storm Arthur are actively producing life-threatening flooding across eastern Louisiana today, with a genuine, if modest, 10% chance of that same system redeveloping into a subtropical or tropical system off the east coast within the next several days. 2 additional disturbances are being tracked across the Pacific, carrying development odds of 20 and 30% respectively. And underlying all of it, NOAA's genuinely new radar research into vertical vortex alignment, built from 27 years of direct hurricane hunter observation, is giving forecasters a meaningfully better tool for anticipating exactly the kind of explosive, Michael-style intensification that has historically caught coastal communities off guard with almost no warning at all. For anyone in Hawaii right now, particularly on the Big Island, given the active hurricane warning already in place, the guidance is direct and urgent. Lala is forecast to cross into hurricane strength specifically as it approaches your island this Saturday, meaning preparation needs to be happening right now, not once the storm's exact peak intensity becomes fully confirmed. Secure outdoor property, review your household's emergency plan, and continue monitoring updates directly from the National Weather Service and the Central Pacific Hurricane Center as this storm makes its final approach over the coming 24 to 48 hours. Given the genuinely small margin, just 9 miles per hour, separating Lala's current intensity from full hurricane status, treat the hurricane warning currently in place as a serious, credible expectation rather than a distant, worst-case possibility. For anyone across eastern Louisiana, southern Georgia, or the Carolinas, Arthur's remnant moisture is producing a genuine active flooding threat today, described specifically as potentially life-threatening in some areas. Avoid driving through flooded roadways under any circumstances, since it takes surprisingly little moving water to sweep a vehicle off the road, and continue checking updated National Weather Service alerts directly, given how the system is expected to continue tracking northeastward over the coming day. And for anyone along the broader eastern seaboard specifically, given the National Hurricane Center's own assessment that conditions could favor some form of redevelopment off the coast by Friday or Saturday, this is a genuinely good moment to review your own hurricane preparedness plan, even with that redevelopment probability currently sitting at a relatively modest 10%, precisely because, as this entire story has demonstrated, the specific storms capable of exploding in strength with very little warning are exactly the ones that a low initial probability or a below-average seasonal outlook can sometimes cause people to underestimate. A storm forming closer to shore in warm nearshore waters, with less distance to travel before reaching a coastline, compresses the entire preparation window dramatically compared to a long track storm crossing the full width of the Atlantic, which is exactly why even a modest development probability for a system already positioned close to the U.S. coastline deserves genuine attention rather than dismissal. This is a genuinely live, rapidly evolving situation across multiple ocean basins simultaneously. We'll keep tracking Lala's approach toward Hawaii, Arthur's remnant flooding threat and potential redevelopment, and both Pacific disturbances closely over the coming days. Subscribe so you don't miss those updates, and if you're anywhere in Hawaii, Louisiana, or along the broader Gulf and East Coast right now, please follow official guidance directly from the National Hurricane Center and your local National Weather Service office rather than relying on secondhand reports. Stay safe, and I'll see you in the next one.